Today I'm going to do a presentation on Qemu support for the Windows Hypervisor on ARM, and more broadly, how to leverage extensibility in the Hyper-V stack. First of all, I'm an engineer at Amazon EC2, and my opinions in this presentation are mine. So for the agenda, I will start by saying what's going on in WSL2 and the Windows subsystem for Android. Then after that, I will talk a bit in detail about the HCS stack which powers this. And after that, I will talk about the Windows Hypervisor Platform, which allows outright to run another VMM. An overview of the stack. So there is the host compute service, which is running as system. There is also the vmwp process, which has the core VMM that's running fully sandboxed. There is support for out-of-process device emulation via VM device host, and that runs in a different privileged context, and it's invoked through Qemu. And the WSL service itself also runs as system. For file sharing between the guest and the host on WSL, that's powered by VirtuoFS. There is an 8 GB shared region for performance. And it can be initialized directly via HCS API so that a third party needing to use that device on their own VMs don't have to deal with custom device emulation. And for Windows guests, the whole VirtuoFS infrastructure is not used, but VSMB instead. So there is a WSL device host. This is an emulation layer for some Virtuo devices, notably VirtuoNet, but no Microsoft product ships with that. There is an implementation of Virtuo PMM. And this component uses VM device host, but it does not leverage VM Virtuo DLL, which also runs on top of VM device host. Then there is a bit of a surprising one for the Windows subsystem for Android. So for the Windows subsystem of for Android, instead of implementing the WSL2 vGPU architecture, a different path was chosen, which was implementing Virtuo GPU with a GFX stream. At this point in time, a Windows subsystem for Android is officially deprecated. So now about the host compute service. There are 3 separate types of Hyper-V partitions that somebody can create on an off-the-shelf Windows installation. There are regular Hyper-V virtual machines which are stateful, with the state being stored inside of the Hyper-V services. This flavor of Hyper-V VMs is only available on professional SKUs onwards. So if you have a home edition of Windows for wide deployment, you can't use the deployment option. Then there are HCS virtual machines. So HCS is available on home editions, so it's available pretty much across the board, but it has close to no good public documentation. And there is the third option, Windows Hypervisor Platform, which allows implementing a custom VMM outright. So this, with the last option, you can actually use Qemu. HCS takes a JSON with virtual machine settings, when running virtual machines because it also supports process isolation containers. Nanabox is a third-party VM launcher tool which uses the HCS APIs. It was a good starting point because it allowed it to easily create an HCS backend virtual machine. Now let's talk about Hyper-V out-of-process device emulation. So for this option, Qemu is used to start the device emulation process across a different security boundary. But you don't have to implement all that stack. So if you run as administrator, you can skip implementing most of this. Then there is vmwp, which is a small layer on top of VM device host implementing a VirtIO-specific infrastructure. It's undocumented, but the VirtIO-FS implementation is built on top of it. Then let's talk about the core component here that is going to be used from that third-party process, which is a VM device host. For the config space, it's fully emulated within VM device host. For the bars, it's a doorbell design where it's possible to trap writes to part of the bars. And then we get a notification event when the guest writes to that bar. The write is not done at that point. So if you do a write and then you try to read right afterwards, the write will not be reflected. The device emulation layer, which is controlled inside of that third-party process, might choose either to reflect that write or not reflect it, which means that it's suitable for implementing something like VirtIO or NVMe, but you can't really implement something like ASCII with the doorbell design. So for supporting it in Qemu, I prototyped the Qemu OOP device binary. So running it as administrator, just attaching. So would it be worthwhile to continue on that route? I don't really know. And if we are going also to support out-of-process arbitrary PCIe devices on Linux, to which extent should it be arbitrary? For example, making writes to bars with doorbells that are async allows to not block the VMM process all the time. So it can be critical from the performance perspective. Now about Windows Hypervisor Platform. So it's an API to support third-party VMMs on Windows without having to run on top of Hyper-V. Only one VM is allowed per process. So let's say you are trying to make something like VTLs. That's not going to work with this API if you try to implement it fully in user mode. And by the way, there are VTL mentions all over the place in the Windows Hypervisor Platform API. But VTLs are not implemented in Windows Hypervisor Platform. It's in preview for ARM64 since Windows 11 version 24H2. And on x86, it has been there since quite a while, and it's implemented on VirtualBox. And it's also implemented in Qemu. So for this one, documentation is not ideal either, but it's not too bad. So for the gig state for Windows Hypervisor Platform on ARM64. So as of the latest public release, which is shipping on Snapdragon XLE devices, there is no way to move the gig MMIO address range to another location. it's fixed at the address for which a regular VM runs, which means that an off-the-shelf QEMU invert machine model is not possible to support in that configuration, which means if we want to support that configuration at this point in time, we have to do a specific Hyper-V machine type. It's addressed in a pre-release build, and it actually works on that pre-release build, but the SDK for that is not currently publicly available yet. And it's a Gig v3 without ITS support. It implements a Gig v3 without ITS, and there is no way to support a third-party interrupt controller for it. So there is no option to use a user mode IRQ chip. So on the hypercall side, the Hyper-V hypercalls are always exposed. And there is no way, for example, to trap SMCs so that they get handled in the custom VMM. So on a regular full-fledged Hyper-V virtual machine, there is VirtIO support available, even as an ITS is not available, because inside of the Hyper-V PCI code, there is an IRQ chip implementation which supports that use case for MSI. So the consequence currently is that VirtIO devices are not functional in the current state of my port. Windows Hypervisor Platform has vPCI specific APIs, but I didn't start using those yet at this point. So on the future plan side, I was planning on getting MSIX working. Maybe those vPCI APIs are the solution. I didn't quite look at those in detail yet. And perhaps writing an mHyper-V target, which is almost the same as mvert, but with a GIC in a different address range, so that users can start testing this today and publish an RFC at some point. So that's it, and I think I went way too fast. So any questions? Oops.
For adding the Hyper-V machine at the end, can you just use the virt machine, and if the hypervisor is Hyper-V, you just change the MMIO range for the geek, so we don't have to maintain another machine on QEMU?
I think it would be possible, yes, but it wouldn't be very standard. So you would get a different representation of mvert depending on the platform on which you run on. I'm not convinced that that's a great idea.
Uh, 24H2 is kind of almost now. So is it really worth to upstream the new machine type instead of just a little bit waiting for the SDK to be published?
So 24H2 currently has this implementation, and the Windows Insider preview has the new fixed implementation. And I can't say myself on when this will be available on 24H2. So no further questions?
Thank you.
Okay.